The most important class of relations for us is going to be the equivalence relations. And in this video, we're going to look at a concept which is defined only for an equivalence relation, and it's called an equivalence class. So let's suppose we have a relation tilde on a set X, which is an equivalence relation. In those circumstances, we define the equivalence class of an element of our set X to be the set of all things Y which are related to X under this equivalence relation. And we then have a piece of standard notation for the equivalence class of an element little x in big X, which is square brackets X, or sometimes square brackets with a subscript tilde, to remind ourselves which equivalence relation we're working with. The only equivalence relation we've seen an example of so far is the equivalence relation of congruence modulo n. So let's look first of all at the equivalence classes under congruence modulo 2. So consider the equivalence relation of congruence modulo 2 on the set of integers. I've written the definition of congruence modulo n at the bottom of the screen there. You'll recall that two integers are congruent modulo 2 if and only if their difference is divisible by 2. So let's work out some equivalence classes. We're going to start with the equivalence class of 0, and we're going to see what this thing is. So equivalence class of 0, this is by definition all y in the set of integers with the property that y is related to 0 under our relation. So y is congruent to 0 mod 2. Okay, well, when is a number congruent to 0 mod 2? Y is congruent to 0 mod 2 if and only if y minus 0 is divisible by 2. So if and only if y is divisible by 2. And another way to put this is just to say that y must be an even integer. So this equivalence class here is simply the set of all even integers. Minus 2, 0, 2, 4, 6, and so on. So that is what the equivalence class of 0 looks like. It just consists of the set of all even integers. Right, let's try a different one. So let's look at the equivalence class of 1 under this relation. By definition, that's the set of all integers y with the property that y is congruent to 1 modulo 2. In other words, it's all the integers y such that y minus 1 is even. But a number minus 1 is even if and only if that number was odd. So the integers y such that y is congruent to 1 mod 2 is exactly all the odd integers. So for example, if you took y to be 3, 3 minus 1 is equal to 2, which is divisible by 2, so 3 is congruent to 1 mod 2. And if you took minus 47 minus 1, then that's equal to minus 48, which is divisible by 2, so minus 47 is congruent to 1 mod 2. And in general, the numbers which are congruent to 1 mod 2 will be precisely the odd integers. So this equivalence class of 1 will consist of all the odd integers. So minus 3, minus 1, 1, 3, and so on. Okay, let's try another one. So what about the equivalence class of minus 2? So again, the definition, this is all the integers y with the property that y is congruent to minus 2 mod 2. In other words, all the integers y such that y plus 2 is even, y minus minus 2 is even. But y plus 2 is even if and only if y is even. So again, this is just the set of even integers. And now something interesting has happened, because two distinct integers have the same equivalence class under our equivalence relation. This is the same as the equivalence class of 0. And I think it's not so difficult to convince yourself that this will also be equal to the equivalence class of any other even integer. And similarly, if we looked, for example, at the equivalence class of 7, well, by definition, that's all the integers y, such that y is congruent to 7 mod 2. But since 7 is odd, y minus 7 is even if and only if y itself is odd. So this will be again the set of all odd integers. And so that's equal to the equivalence class of 1. And once more, I think you can convince yourself without too much difficulty that this will be the same as the equivalence class of any other odd integer. So what it turned out was that for this equivalence relation of congruence modulo 2, there were only two different equivalence classes. And what's more, those equivalence classes split the integers up into two disjoint pieces, the odd numbers and the even numbers, with nothing in common between them. So what we're going to find out as we study equivalence classes further is that this property persists for all different kinds of equivalence relations.